here, folks. We are going to pick up where we left off talking about polynomials. But before we move forward, let's just kind of do a little bit of a refresher here about what we did last week with regard to polynomials, since it's been a couple of days. So we'll do some examples. So, is this a polynomial? What do you guys think? Yes, okay. So, yes is the correct answer. Why? Okay, so that was, I think what you're talking about is standard form for a polynomial, but that you could order the exponents from greatest to least and have something still not be a polynomial. What did we look for here to determine that this was a polynomial? It is, so you're right on that regard. I'm just trying to dig a little bit deeper and refresh our memory as to what we're needing to look for. Harley? So the exponents have to be whole numbers. Yup. And what else do the exponents have to be? Positive whole numbers, right? So if the exponents on the variables are positive whole numbers, you should be good to go. Well, the only operations can be like addition, subtraction, multiplication. But like you can't toss like a square root or absolute value or something in there. Around the x's anyways. You can put them around the numbers, that's okay. So let's say we have this fella here. Is this a polynomial? No. Okay, why not? So we have a negative exponent. Is there any other reasons it might not be a polynomial? So the exponent of 1/2, is the square root of 7 a problem? Yeah, that's just a number, so that's okay. Now, what wouldn't be okay is if it was this, and the square root was around the variable also. This is not okay. But you can have a square root around a coefficient. That's all right. Just can't extend over the variable. Cool? We remember what a polynomial is? Yeah. Okay. All right, so for the next example, you're going to write the polynomial in standard form and then list the degree for the polynomial, the leading term, leading coefficient, constant term, and number of terms. So here's our polynomial. If I want to write this in standard form, what do I write first? 7x to the 5th. Good. Why did that one come first? biggest exponent comes first, exactly right. Okay, then what? Very good, negative 13x to the third. And then negative 2x squared, and then 10x, and then obviously the plus 8 is the only thing left, so that has to be last. This is standard form where we've just written the exponents from biggest to smallest. Everybody's good with that? Okay. What's the degree for this polynomial? 5. Good. How'd you find that? It's the biggest exponent on the terms, right? That's fine. The leading term is 7x to the fifth. And the leading coefficient then is 7. What's up? It's the first one when you write it in standard form. It's the one with the biggest exponent. Yep. What's the constant term? Eight. Right? The piece with no variable on it. And then the number of terms we got is 5. I got 1, 2, 3, 4, 5 terms. Everybody feel okay there? So, what if we ask you to simplify the expression f plus g of x with the f of x's and g of x's that I've described here above? How would I do f plus g of x like that? Do we do the grid for addition? No, right? What do we do for addition? No, there's no substitution that we need to do here. Just going to combine the like terms, right? So if I look, there's nothing to pair with the x to the fourths, or the x to the thirds, or the x squareds. We do have two different x's. I have x and negative 3x, so when I add those together, I get negative 2x. And then I have negative 2 and positive 1. When I add those together, I get negative 1. And typically when we write the answers, we'd write them in standard form like I've done there, right? What if I do f minus g? Nope, we're still not going to do the grid here. We're going to combine like terms, but we've got to be a little bit careful here because of the subtraction. Really what we have to make sure of is that when we do this subtraction, that negative sign distributes to everything in the second polynomial. So when I do that, the x squared becomes negative. The 3x then becomes positive, and the 1 becomes negative. And now I'll combine my like terms. Everybody okay there? Oh, that's a typo. Thanks, Tommy. Everybody good with that? Again, not too terribly tricky, right? A little bit similar to when we subtracted complex numbers. We had to make sure we distributed the negative there also, right? We talked about not that long ago. What if I wanted to do f times g of x? This is the one where we do the grid, right? Okay. So the way we set that grid up is we're going to write one of the two polynomials, it doesn't matter which one, along the top of the grid. But I'm going to remember to make sure to put the zeros in. So notice that this is missing the x squareds. So where the was supposed to be x squareds, I'm going to put a 0 there. Yeah, for f, because if you look here, we're going from x cubed to just x's, and we missed the x squareds. So there's none of those, right? There's 0 x squareds in that part. So that's why I put the 0 there. So there's my setup for my grid. And now I'm going to just do each of these little multiplication problems. So I have x to the 4th times x squared. That gives me x to the 6th. And then x squared times negative 5x to the 3rd. That's negative 5x to the 5th. And I just keep on going, so on and so forth, until I fill the grid out. Worth noting, observe the pattern here as we go from left to right. If you look at the exponents, they're all decreasing by 1 each time. Now, if you had not included the 0 there, that you would not get that pattern. Just as a heads up. Also look up and down the grid. You also see the pattern that the exponent is decreasing each, or by 1 each time. Again, if you didn't put the zeros in there, you'd lose that. So I did x times x, which is x to the 3rd. Yeah, so the exponent on x is just 1. Everybody's, Harley? Okay. So we did negative 2 minus a positive 1, which is the same thing as negative 2 plus a negative 1. And that's why we got the negative 3. So, yep. So just got to, once we've distributed that negative, we're done doing subtraction anymore. Now it's just like adding. Does that make sense? Okay. Sure. Yeah. The 0 could be anywhere if it's missing. If you have the x before it, and you don't have the x after it, you put a 0 coefficient there. So you might have 2 or 3 or 4 of them in a row even, like that's possible. Okay. So now we'll just combine like terms. The nice part about this is that the like terms are organized along the diagonals. So I have just x to the 6th, and I have negative 3x to the 5th and negative 5x to the 5th to give me negative 8x to the 5th. And then I have x to the 4th, 15x to the 4th, and then 0 to give me 16x to the 4th. I have negative 5x to the third, 0, and 1x to the third to give me negative 4x to the thirds. 0, negative 3x squared, negative 2x squared gives me negative 5x squared. X and 6x gives me 7x, and then just the negative 2 at the end. So that would be my final answer. Everybody okay with how I collected the things from the grid and turned it into the final answer? Yes, John. So this is what G was, and that was what F was. So when you go back to the very beginning when I said what F and G was, I just used those. Is that what you're asking? You're good? Okay. Does it matter which one I put where? It does not matter, right? You could do F as the one going up and down and G the one going left and right. It doesn't matter. Because what are we really, from a geometric sense, what are we doing here? We're computing an area, right? Just doing length times width. Right? You can compute the area of a big rectangle by dividing it up into a bunch of little rectangles, adding those up. That's basically all we're doing here. So, today we're going to talk about two things. The first thing is called synthetic substitution. And then after we talk about that, we're going to talk about polynomial long division. So let's say that we have the polynomial f of x is equal to negative 2x cubed plus 7x squared minus 5x plus 1. And we want to evaluate f of negative 1. What does that mean when I say compute f of negative 1 like that? This is an Algebra 1 question. This means plug negative 1 in for x and get the, I don't know, answer, whatever. So where are we plugging negative 1 in for? The x is in my polynomial f. So f of negative 1 would be negative 2 times negative 1 to the third plus 7 times negative 1 squared minus 5 times negative 1 plus 1. Everybody's okay with that? So if I go to simplify this now, negative 1 to the third is negative 1 times negative 1 times negative 1. Negative 1 times negative 1 is positive 1, and positive 1 times negative 1 is negative 1. Negative 1 squared is negative 1 times negative 1, which is positive 1. Negative 5 times negative 1 is positive 5. And then negative 2 times negative 1 is positive 2. 7 times 1 is 7. And if I add these together, I get 15. Everybody kind of remember doing this from your Algebra 1 class? This is the same thing we do like when we're graphing, right? We pick a value for x and then we plug it in to find the y value. Same idea here. Harley? Because the order of operations says that we do the exponent before we do the multiplication. So this is really negative 2 times x to the third. So the exponent is applying only to the x. And then we'd multiply it by the number out front. Does that make sense? Okay. Good questions. So this is just substitution, right? We haven't done anything synthetically. We can do the same problem doing synthetic substitution. So, to do that, the way we set this up is we start by drawing this kind of a bar, just to kind of organize what we're going to do here. If we're doing f of negative 1, just like we did before, I start by writing the negative 1 over there. And then inside the bar, I'm going to write the numbers negative 2, 7, negative 5, and 1, because these are the coefficients from f. Everybody see that? So far, so good? All right. So that's the setup. I just write whatever we're substituting in for x on the outside, and the coefficients for my polynomial there on the inside. The first step of this process is to just take that first number and write it underneath the bar, like we've done there. And now what we're going to do is take negative 1, multiply it by this negative 2, and then write the answer above the bar, and then add down. Is everybody okay with that? Harley? Well, negative 1 times negative 2 is positive 2, right? So the negatives cancel each other out, so to speak. Now I'm going to just continue. I'm going to do this same process until I've run out of spaces. So we'll do negative 1 times 9, and then we'll write the answer right there. And we'll add down. When I do that, I get negative 14. And we still have one more space left, right? So we'll do this one more time. We'll do negative 1 times negative 14. That gives me 14. And when I add down, I get 15. It's this last number that we care about. That's our value for f of negative 1. Note that that matched what we got above using our Algebra 1 method. Everybody see that? That we got the same answer, doing the problem in 2 different ways? And now, yes? Not that you would do, no, but it's could be. Okay. Okay. So the question is, okay, what's wrong with doing it the Algebra 1 way? Right? It seems like it's no less work to do this synthetic substitution thing. We're doing the same thing. Why invent a new method? Right? That's a perfectly reasonable response to seeing this. Like, why do I have to learn something new when the other way works just fine? It does, and it will continue to work just fine. The reason we're showing you this method is that this method I can use in a number of different settings to do things other than just substituting values in for x. And there it's going to work really nicely for us, because it turns out that these other numbers down here, and even this number at the end, have some other meanings that we'll get to a little bit later this chapter. And with really almost no modification, we can use this same technique to do other things that'll be really useful to us. That this makes it a big shortcut to do it on the, or to use this to do those other things in the future. So right now I want us to just get used to and get comfortable with this technique, doing this very simple substitution exercise, because it's something we already know how to do the long way, right? Or the Algebra 1 way, maybe I should call it. And that's allows you to kind of check your answer and get a feel for, like, okay, it's doing the same thing as what I already kind of knew how to do. Let's do one more. So let's say we have the g of x that is equal to 3x cubed minus 7x plus 8, and I want to do g of negative 2. So I'll start by drawing my bar. What number is going to go on the outside? Negative 2 goes on the outside. And what are the numbers that are going to go on the inside? Tell me. So we'd think this, right? It's not quite right. We're missing something. There should be something in between the 3 and the negative 7. A 0. Why would I put a 0 there? I went from x cubed to x's. What did I skip? X squareds. So I need to make sure I put a 0 there for the x squared spot. Okay? Just like when we drew the grid, we included those zeros when we skipped terms in our standard form polynomial. We're going to do the same thing here. You absolutely need to include the zeros, or this will not work. Everybody's okay so far? All right. Let's begin then. So I start by bringing down the 3, and then negative 2 times 3 gives me negative 6. And when I add down, I get negative 6 still. Then negative 2 times 6 gives me positive 12. I add down, and I get 5. And then negative 2 times 5 is negative 10. And when I add down, I get negative 2. And that's what I'm interested in. So, somewhat surprisingly, g of negative 2 is negative 2. Is that common? No, right? You wouldn't expect to get the same thing that you plugged in to come out. That's just like a happy accident here. What do you guys think about this synthetic substitution? It's not too bad, right? All you have to do is do a little multiplication and addition and be able to set the thing up, and then it's not too bad. Just got to remember that little procedure, but it's not too bad of a procedure, right? Okay. So the next topic that we'll talk about is polynomial long division. And before I start talking about this, I need to ask you guys, how many of us know how to do regular number long division? This used to be not a question I had to ask, but it seems like some schools are doing a little bit less of this instruction than others. Okay. So let's do an example here of regular, like numeric long division to just kind of get our memories jogged. So let's say we want to divide, I don't know, 3,476 divided by, I don't know, like 19 or something. Okay. So just as a little bit of vocab review, this number was called the dividend, and this number is called the divisor. So when we set up our problem, what number goes on the outside of our division bar? The divisor. And what goes underneath? The dividend. Okay. Everybody kind of remember that? Okay. All right, so then we ask ourselves, how many times does 19 go into 3? Well, 0. Okay, so then we ask, how many times does 19 go into 34? 1 time, right? So then I do 1 times 19, write it under the 34, and we subtract down. So 34 minus 19 is 15, and then we bring down the next digit. You guys kind of remember this right now? Okay. So we do the same thing. We ask, how many times does 19 go into 157? It should be 8, I think. 19 is almost 20, right? And 20 times 8 is almost 20 times 8 is 160. Or it should be, that should be good, right? 8 times. If I do 8 times 19, I get 152. And then I subtract down. And then I bring my next digit down. And I ask again, like, how many times does 19 go into 56? Yeah, 2 or 3. Do we know which one? 2. 2 times 19 is 38. When I subtract down, I get 18. So at the end, we would write remainder 18. Everybody kind of remember doing this? But this is not the way we like to write our final answer, right? So what we said for our final answer then to this problem is this is equal to 182 plus 18 19ths. So remember that this number is called the quotient. Here is our remainder, and this is the divisor once again. Everybody okay there? So let's try doing this with polynomials now, that we've kind of refreshed our memory. So let's say we want to divide x cubed plus 6x squared plus 11x plus 7 by x plus 2. Okay. Well, we'll set this up the same way we did before. We'll draw our division bar. We'll write the divisor on the outside and the dividend on the inside. And now polynomial division is almost, I think, in a way, easier than long division, because it's easier to figure out what the values in the quotient need to be. Because in polynomial long division, all I care about are the leading terms. So I'm just going to ask myself, what times x gives me x cubed? What times x gives me x cubed? X squared, right? X squared times x is x cubed. Everybody good with that? So then I take that x squared and I multiply it to everything in the divisor, and I write it underneath the dividend, and then we're going to subtract down. Now, this is the place where we have to be really careful as students. Notice that I put this parenthesis around the x cubed plus 2x squared. And there's a minus sign out front of that. What does that mean we're going to have to remember to do? I have to distribute that negative. So I'm going to erase these parentheses and do that distributing. So the positive x cubed becomes negative, and the positive 2x squared becomes negative, and now we're just going to add straight down. So x cubed plus negative x cubed is 0, and 6x squared plus negative 2x squared is 4x squared, and then we'll bring the next digit down, or the next term down. And we're going to do it again. We're going to ask what times x gives me 4x squared. Very good. So we'll write plus 4x there. And then we're going to multiply that 4x by everything in the divisor. That'll give me 4x squared plus 8x, and then I subtract. But remember, we need to do what with that subtraction? Distribute it. So really I have negative 4x minus 8x. Everybody good with that? If we add down, 4x squared plus a negative 4x squared is 0. 11x plus a negative 8x is 3x. And then we bring the next term down. And one more time we ask, what times x gives me 3x? 3. So I'll write a plus 3 up here. And then I multiply that to each part of my divisor. That gives me 3x plus 6. And I'll subtract down. Remember, since I have that subtraction symbol around the parenthesis, I need to distribute. So really I have a negative 3x and a negative 6. And when I add down, I'm left with 1. So my quotient is x squared plus 4x plus 3, remainder 1. But that's not how I'm going to write my final answer. I'm going to write my final answer as quotient plus remainder over divisor. And that's the way that we'd want to write our final answer. Everybody okay with that one? That shouldn't have been too bad, right? Let's do another, okay? Hopefully you guys see the similarities between this process and the long division you learned in elementary school, right? Very similar. So let's say we want to do x cubed plus 8 divided by x squared minus 2x plus 4. So let's set this up. We'll draw our division bar. What's going to go on the outside of the division bar? Not x cubed plus 8. On the outside of the division bar should be the divisor, x squared minus 2x plus 4. And what should go under the division bar? X cubed plus 8. But I'm not going to write it like x cubed plus 8. How would I write it? I'm going to write it as x cubed plus 0x squared plus 0x plus 8. Because I want to make sure that everything lines up. Is it necessary that I put the zeros in for these problems? For this problem, not technically, but in my experience, if students don't put the zeros in, they make mistakes. What they end up doing more often than not is combining things that are not like terms, because they have things that aren't like terms lined up to subtract during the subtraction problem, and then they make a mess out of things. Put the zeros in, things go much better. Okay, so we're going to ask ourselves, what times x squared gives us x cubed? X. Good. Then I'll multiply that x to all parts of the divisor. Too many D words here. And we'll subtract down. So, when I have this subtraction, what am I going to do? I'm going to make sure I distribute that. Yeah, so the x cubed becomes negative. The negative 2x squared becomes positive. And the positive 4x becomes negative. So I'm left with 2x squared minus 4x. And then we'll bring that 8 down. Oops, I've been writing these in red. Everybody okay with that step? Okay. You say what times x squared gives me 2x squared? 2, right? So I'll put a plus 2 there, and I'll multiply the 2 to all parts of my divisor. Do I really need to distribute the negative to see what this subtraction problem is going to give me? What's it going to give me? 0, right? Yeah, because you have the polynomial subtracted by itself. Oh, yeah, it's going to be 0. So do we need to bother writing remainder 0 here? No. What would the answer for this be? Just x plus 2, right? Everybody's okay with that? Okay. Let's do one more, and then we'll call it a day. What do you say? Sound good to you guys? Okay. So let's say we're going to do x to the fifth minus 4x to the fourth plus 2x cubed plus 2x squared plus x plus 6 divided by x squared plus 1. What's going to go on the outside? X cubed plus 1? So I'm not going to write x squared plus 1 as x squared plus 1. How would I write that instead? X squared plus 0x plus 1. I do that so when I do my multiplications, I make sure everything lines up with like terms. So if we go back to this previous problem, if I didn't include the zeros there, I'd have plus 8 here, and I'd be tempted to try to subtract or combine 8 and 2x squared, which are not like terms, right? You see that? So we put those zeros in there to make sure that everything that's lines up underneath a like term. So if I don't put the zeros there, it gets a little bit confusing as to like what am I supposed to be adding and subtracting together. That's why that's really important that we remember to do that. Now, if you're really paying close attention, it's probably fine, but in my experience, this procedure is long enough for most students that they don't need the extra level of like, I got to be careful about this thing now because I didn't put the zeros in. If you put the zeros in, it's a little less paying attention that you have to do because everything lines up for you already. Does that make sense, Sean? All right, so let's start this one. So I'm going to ask what times x squared gives me x to the fifth, x to the third. Everybody agree with that? So I'll multiply that to all 3 parts of my divisor. And then we subtract down. So I'm going to make sure to distribute that negative. So negative, negative, negative. That's going to give me negative 4x to the fourth plus x cubed. And then I'll bring that next digit down. Yes, sir. Of course. So next step, what times x squared gives me negative 4x to the fourth negative 4x squared. Everybody agree with that? And then I'll multiply that to all the parts of the divisor. And then let's distribute that negative. So that becomes a positive. That becomes a negative. That one becomes a positive. So I have x cubed plus 6x squared. And we'll bring that plus x down. Everybody still doing okay? So what times x squared gives us x cubed? X. Good. And then when I distribute this to all three pieces, I get x cubed plus 0x squared plus x. And I subtract down. Got to make sure I distribute that negative. So negative, negative, negative. So I'm left with 6x squared plus 0x. And then I'll bring down that plus 6. Notice that I still wrote a 0x there. Again, I don't usually write the zeros if it's the first thing, but if there's something in between two terms, definitely want to make sure I put the 0 there. Again, just to make sure things line up correctly. Yeah, Juan? Sure. It's because I saw it x squareds and then a constant, but there's no x's in between. Exactly, because I skipped a term in there. Does that make sense? So that's all I'm looking for, is if there's like, if you skipped something. Okay. So my last step here then, what times x squared gives me 6x squared? 6! And when I multiply that to all three pieces, I get 6x squared plus 0x plus 6. And when I subtract down, we should easily see that we get 0. So the answer to this problem we'd write is x cubed minus 4x squared plus x plus 6. And that's it. And we're done here for today.